Hey everybody, welcome to your last new day of new instruction in Physics B. After today, that'll be it. We will review for your exam tomorrow. We'll take our test on Thursday. So enjoy it. And it's a good day to end on. Today is one of my favorite days to really talk about. I'm kind of bummed that I can't be there in person for it, but it's going to be good. So have your study guides open and let's get started. So let's do a quick little recap of what we did at the end of yesterday. At the end of yesterday, we constructed arguments for what is light. We made a claim that light is a wave. We provided a lot of evidence, at least, let's see, diffraction, emission, absorption, reflection, refraction, interference. That's at least six forms of evidence here. I think we focused on, in our reasoning, two of them, that being diffraction and interference. So just to remind you, your claim is a claim, a statement of what you think. Evidence would be supporting information. Reasoning, again, is the justification that connects the claim to the evidence. So in the reasoning here on this page, we focused on why is diffraction evidence that light is a wave? Why is interference evidence that light is a wave? And so I showed, hopefully, I think everybody did it, but here's my example. So I said, my claim is light is a wave. The evidence is interference. Reasoning, interference is a property of all waves that allows waves to pass through each other and combine amplitudes. I just realized I wrote combing, but that should say combining. Light is capable of interference. I know this because I observed what we call the double slit experiment. Provide a diagram if I want. And then because light can interfere, it must be a wave. I think that's a well-written and good constructed argument. Then we started on this page. Sorry, let me see if I can move this out of the way. So this is page 8. So we took a look at some history, right? And kind of just to keep track of how far we've got to this point. On page 8, part A, it talks about Isaac Newton, an ancient Greek named Empedocles, and the Dutch physicist Christian Huygens, who lived at the same time as Newton, as well as Thomas Young, who came a little bit after Newton and Huygens. For part A, we have Isaac Newton, who was a proponent that light was a stream of particles. We have Empedocles and Christian Huygens, who are proponents that light is a wave. This is a very old and very, you might call it heated debate in the scientific community at the time. But really, in 1801, Thomas Young really, I would say, kind of put the nail in the coffin, kind of put this debate to bed, that light is a wave because it interferes. This was by far the most concrete and dramatic evidence that light was a wave. And so the debate was over, or so we thought. Time goes on, technology improves, people discover new things. And Albert Einstein was one of those individuals who, again, came after Thomas Young. So he knew about Thomas Young and he knew about his experiments. Albert Einstein was not trying to dispute that. He was not trying to say that light was not a wave. He simply found something. And that's the nature of science. When new things are found, we have to reopen some old arguments. We have to take into account that evidence and revise our ideas. And so I think we just ended with this yesterday. Albert Einstein and others discovered in the early 20th century, the early 1900s, that yes, light behaves like a wave in many circumstances, but on small scales, low amplitude dim light doesn't act like a wave. In fact, it acts more like a particle because it doesn't deliver energy continuously like a wave does. Instead, it delivers wave in discrete chunks that we call quanta, like a particle does. Albert Einstein described light as a wave, but also small particles. And I want to make that point clear. Albert Einstein, again, is not trying to throw the wave nature of light out the window. He recognizes that that is a fact, it's observable evidence. But he also is recognizing that there is a particle-like nature of light. And so Albert Einstein is one of the first to really describe light as having a duality, a particle-like nature and a wave-like nature. You can all be writing this down on page 8, by the way, where it says down here, part D, how did Albert Einstein describe light? Again, this is one of the first individuals to really describe light as having a duality, both a particle and a wave-like nature. He called these particles of light photons. One of his big experiments that he did was called the photoelectric effect, where he found that photons of a very particular energy level were able to remove electrons from the surface of metals. It was almost like billiard balls bumping into each other. He called it the photoelectric effect. When I was in college, I was able to recreate Thomas Young's double slit experiment using a laser pointer and various different mirrors and beam splitters. It is complicated, but it's the reason it looks like this is because this laser pointer and this measuring device over here are designed to fire one photon of light at a time through a double slit located right over here. That's the point of this experiment. Same idea as Thomas Young had, 2 slits with light, but this time we're trying to fire one photon at a time. And if you think about photons being particles of light, then the double slit experiment kind of loses its meaning almost, because the double slit experiment was meant to show the wave nature of light. But if we think of light as a particle, then when light would, if light were a particle and it were to pass through the double slit, then it wouldn't behave like a wave anymore. We would think of it like the analogy I used yesterday, like firing tennis balls at 2 doorways. The tennis ball, a single tennis ball, really has one of 3 options. It either goes through one door, the door on the left, it goes through the door on the right, or it hits the solid piece of wood in between the doors. It can't go through at all. That's typically what we think of when we think of light as a particle. And so Albert Einstein and many others, and myself when I was in college, if I had this setup, I would love to do it in class with you guys, but they set the experiment again. Single photon, double slit experiment. And I'm going to show a brief video, and this video is something of a time lapse, if that makes sense. It's going to show single photons being fired through a double slit at what's called a photocollecting plate. And this plate will show where single photons land on this plate. So these little points of brightness are where photons are landing. You can see down here kind of as time goes on, the number of photons is increasing. And it's going to show what happens when we fire one photon at a time at a double slit. Again, it doesn't make a whole lot of sense because we expect light as photons to be behaving as particles. And so, like we talked about yesterday, we expect kind of 2 bright bands where the photons had a possibility of going through. So I'll play the time lapse and I'll kind of let you see for yourself what happens. See down here, the total number of photons is growing. Initially, the pattern doesn't seem to have much to it, but as time goes on, I think something very clear emerges. Oh, we just missed it. Sorry, I'll go back. Take a look at that for a minute. Turn to your partner. What do you see? What does this look like? I'm betting money you didn't actually say anything to your partner, but you know, I can hope, can't I? Hopefully, at least you're thinking that this does not look like 2 bright bands where a tennis ball or a photon of light could go through one door or the other. This is an interference pattern. Even when we fire one particle of light at a time at a double slit, it still acts like a wave. And so we have to really broaden our minds just a bit and really accept what we're actually saying by looking at this. Not only are we saying that a particle of light is acting like a wave, it is interfering. Literally, that's what this is. And it's interfering with itself. What does that mean? Well, what it means is as we fire this photon and it approaches the double slit, you ask yourself, well, which slit did it go through? The slit on the left or the slit on the right? If it were acting like a particle, we would be able to pick one, but it's not. This single photon of light is acting like a wave, which means that it's not going through the left or the right. It is actually going through both. I'm going to give you a second, let that sink in. This single photon of light is somehow going through both slits at the same time. And then it gets even weirder. Then, once it gets on the other side, again, it is interfering with itself. It knows somehow or other not to land in one of two discrete bands, but instead to land either here in a central spot, or here, or here, or here, or here, or here, or here. But it also somehow knows to not really end up in the spaces between them. It knows the appropriate places of constructive and destructive interference, where to land and where not to land. This is incredible. It was revolutionary. It shook the very foundations of science and everything we knew about reality. And if you think this is weird, believe me, it gets weirder. Like I just said, this photon is somehow in both slits at the same time. It is somehow in two places at once. So, scientists were like, is it really? Come on, is it really? Let's measure it. Let's observe it. Let's put a little detector by these two slits. And that way, when the photon enters those slits, both detectors should go off at the same time because they both should say, yep, photon's there. And so that's what they did. They set up the same experiment, but this time with a detector in place. Exact same setup. Same laser, same double slit, same little photo collecting plate at the back. All they did was add a detector to tell them, yeah, the photon's in the same place at the same time. So here's the same experiment, this time with detectors. I'm smiling because I'm hoping that as you watch this, you're thinking in your mind, WTF? What? And I know some of you like to accuse me of like acting when I get in front of you guys and I try to pretend like I don't know stuff. True, I act sometimes, but I'm not acting right now. I've seen this a million times and I still am in complete disbelief when I see it, right? This is very clearly not an interference pattern. This is two bright bands. This is what we expected to see way back with Thomas Young's experiment, before we really thought light could interfere. Let's break this down for a second. When we set up the single photon double slit experiment, that single photon somehow still acted like a wave and interfered. But now we didn't change anything about the setup except we installed little detectors to really confirm, yep, the photon's in both slits at the same time. And what did the photon do? The photon stopped acting like a wave. It completely stopped. We end up with this setup and the detectors. What do you think the detector said? Do you think the detectors said that the photon is in both slits at the same time? They didn't. The photons now tell us that the photon, as it approached the single slit, chose one or the other. It either went to the left or it went to the right, and then landed right here or right here. Somehow, some way. We still really don't know why, but somehow this photon knew that it was being watched. And as soon as it knew that it was being watched, as soon as we tried to watch it, it changed its behavior. And you could go the other way. You could take this setup and remove the detectors, take them out, stop watching. And as soon as you do, this pattern disappears and the interference pattern comes back. As soon as we stop watching the light, it behaves like a wave again. This phenomenon is so mind-boggling but popular enough that it is the subject of countless memes. And so you're welcome, by the way. You get to see some of the best top tier memes in all of existence, and you're going to laugh at them. And I really wish I could be there to see you laugh at them. So here's one. Let me move this out of the way so you can see it. They're amazing. Here's another. A lot of these are SpongeBob themed. I like SpongeBob. Here's another. Here's another. I didn't make these, by the way. These are just on the internet. Last one, I promise. Okay. Let's take a second and maybe define everything that we've seen so far. Let me bring this slide down so we can use it. Let's head over to, actually, no, let's not use page 8 for this. Let's use page 7 for this. So right here in page 7, let's kind of jot down everything we've seen so far with regards to duality. I think it's helpful to make some sketches. And these sketches are honestly going to be very similar to the sketches of the double slit experiment. You can find a sketch of that on page 8, or you likely drew one yourself on page 5. And I would draw two variations of this. You're going to have a laser pointer or some kind of light source, but remember, it's one photon at a time. Going or passing or approaching a double slit. In one instance, we're going to have no detectors present. So let's say in my first case right over here, this is a double slit experiment with no detectors. So that'll be my top half picture. On the other side, on the screen, on the photo collecting plate, what pattern do we see? We see an interference. Again, no detectors, interference. Light acts like a wave. It's probably good to label these two. In the second drawing, I'll probably draw this on the bottom half here. I'll draw the exact same setup. Laser pointer, single photon, double slit, but this time I'm just going to draw detectors. However you want to represent that is up to you. You can draw like a little box right next to the slits. It's not important how you draw it, but point is we're watching the slits now. We're watching the photon. And most importantly, you want to draw it kind of over here. What do you see? What is the pattern? This time it's not interference. It's just two bright bands that are kind of right behind those slits. And you might label the bottom picture particle behavior and the top picture interference / wave behavior. Okay. If the sub would like to pause the video right now to kind of give you guys time to draw, I think that'd be appropriate. Yeah, hopefully you have those pictures drawn. One more thing I wanted to show you. This bizarre world of light, as we've seen, light is unlike anything we've ever dealt with before. In our experience, things are either particles or waves, but for unknown reasons, light can somehow act like both. And depending on the circumstances it is in, it will choose which one to act like. But later, later in time after this was discovered about light, scientists began to wonder about other things. Perhaps there was a flaw in this experiment somehow. And so they repeated the experiment, but this time, instead of firing single photons, they fired single electrons. Now, we haven't talked a ton about electrons in this class. You will if you go take chemistry, but we have a little bit. We know electrons are a part of the atom. They're these little negatively charged particles. They have mass. That's something, right? Photon, and I know a few of us have mentioned this before, but a photon, a particle of light, does not have any mass. And I mean that literally. It has zero mass, it is massless, but it can deliver energy. It has momentum, but it doesn't have mass. Electrons, on the other hand, have mass. It's a very small amount of mass, but it is something, it has mass. And so we always think of it as a particle. In all these drawings that we see of atoms, it's this little tiny ball that kind of whirls around the nucleus. Some drawings are a little bit more scientifically accurate than others, but for our purposes, it's okay. And so that's what they did. They repeated the double slit experiment, but they removed the photon, the laser pointer that fires photons, and instead they installed something that is capable of firing single electrons. Same setup, firing single electrons at a double slit, and they took a look at what happened. So I wanted to take a look and see what we can find. Same setup, this time it's just electrons. And the same kind of setup here. Each point of brightness that you see appear is going to be a single electron showing up, kind of marking where it pops up on the screen. Time lapse kind of speeds up. Similar to light, initially there isn't much of a pattern, but as time goes on, I feel like I start to see a pattern emerge. Go ahead and pause it right there. Turn to your partner. What pattern do you see here? Hopefully, you at least thought in your mind, but even better if you said it to the person next to you. This is also an interference pattern. What this experiment shows, and this is where things just continue to break my brain every time I think about it. What this experiment has shown is that even a particle like an electron, something that we know about, that we are familiar with, something that has mass, even this particle acts like a wave. It interferes, just like a photon does. A single electron fired at a double slit will pass through both slits at the same time, will interfere with itself, and then will land in a place that corresponds to constructive interference, but will generally avoid an area of destructive interference. This experiment, this double slit experiment, both with light and with things like electrons, is really the foundation, the cornerstone of an entire branch of physics called quantum mechanics or quantum physics, the study of the very small. It is an entirely different world because things at this scale. Sorry, there's an ambulance going by outside. This world of the very small behaves completely differently than our world. In our world, things are either particles or waves. In this world, everything is both. Everything can have properties of both particles and waves. Just to show you a little bit here, generally we can map position, we can talk about velocity, we can talk about acceleration and forces when we look at particles in our everyday experience. These are some equations that you've used before. But when we talk about electrons or photons that most of the time don't act like particles, they actually act like waves, then to describe their position and their motion is a whole lot more complicated. I'm going to play this short 1-minute video.
The Schrödinger equation is the key equation in quantum physics that explains how particles in quantum physics behave. You want to know where your electron's going to go? That's the Schrödinger equation you'll need. So why does it look so complicated? Well, it's because in quantum physics, when you're describing what a thing like an electron will do, it doesn't follow the rules of particles, it follows the rules of waves. And that's what these psi's are, they're wave functions. Okay, so an electron is a wave, and a wave can evolve in space and in time. But it can't evolve in any old way. There are constraints about how it can evolve, and those constraints, that's what the Schrodinger equation is telling us. It says that over time, that's this bit, the total energy has to stay the same. And this total energy is made of the kinetic energy, that's this bit, and the potential energy, that's that bit. An example for a potential energy for an electron is just being in an atom. So if you want to see what a quantum object will do in the future, you need to find the wave function that will satisfy all of these bits of the Schrodinger equation.
I just wanted to show you how just freaky that equation looks.
The Schrodinger equation.
Get out of this. When I was in college, I took 3 kind of more intermediate and advanced physics courses, and in one of them, I very briefly got to touch this equation. I got to kind of see its parts, and it was never something I actually like really used in depth, but it is something I was able to kind of break down and look at kind of the parts of it. If you ever go to college and you get to take linear algebra and differential equations, that's exactly what this is. It's hard math. I'm somebody who likes math, but this is hard. This was tough for me anyway. So maybe you'll go on and you'll love it. But yeah, this is quantum. This is how things work. Things at this scale are dual in nature. So let's head back over here. What I'd like to do on page 7 of your study guide, if you're not there, you can kind of flip over there. Hopefully by now you have some investigation notes here. You should have 2 drawings, right? One drawing of the double slit experiment with no detectors, where we see interference. Another drawing of the double slit experiment with detectors, where we see no interference. The top picture shows wave nature. The bottom picture shows particle nature. And that really is the definition of what we call duality. So if you'd like to write that definition down on page 7, you're more than welcome to. It's probably a good idea. Again, the phrase, or not phrase, the term we're interested in is called duality. And duality, simply defined, is the fact that light can behave as both a wave and a particle. And so with that, I would like to do something similar to what we did yesterday. I would like to update our claim evidence reasoning. Yesterday, our claim was that light is a wave because of interference and diffraction, and we included some reasoning. I'd like to update that claim because we have to. We are forced to as scientists. We have to update our claims. And so now our new claim should say something like light is both a wave and a particle, or light is dual in nature. Our evidence, this is where we're going to cite the experiment we witnessed, and that would be, to sum it up, I would call it the single photon double slit experiment. I'll say that one more time. You can write it down here in the evidence. The single photon double slit experiment. And then you can include with/without detectors, because that's really the 2 variations of it. And then down here in the reasoning, that's where we want to tie this to this. Why is the single photon double slit experiment evidence that light has dual nature, is both a wave and a particle? So I'm going to let the sub pause the video here for a minute, maybe 2 minutes, and allow you to kind of write down your reasoning. After that 30 seconds, minute, 2 minutes is up, they can unpause and I'll kind of show you what I wrote. So I'll let them pause now. All right, hopefully everybody's got that written down. I'll kind of show you what I wrote. So my claim, light is a wave and a particle, or I could phrase that as light has duality. My evidence is the single photon double slit experiment. Reasoning. When a single photon, particle of light, is fired at a double slit with no detector present, the photon interferes. This is evidence that light, or photons, are waves. When a single photon is fired at a double slit with detectors, then the photon does not interfere. And this is evidence that photons, or light, are particles. Because light can behave as a wave or a particle under different conditions, this demonstrates the duality of light. If you'd like to update yours or add anything to it, feel free to do so. This brings us to really the last little bit of this duality discussion, and that is this image. If you look on the bottom, I think it's the bottom left or the bottom right corner of page 8. Looks like the bottom right corner. Yours is in black and white, but this is what the image actually looks like. It's a strange looking picture. I will totally give you that, but I want to talk about what it is. This is a recent picture, and by recent, I mean within the last 20 years. This is actually captured in the year 2015. From the early 20th century with Albert Einstein all the way up to about 2015, the duality of light was pretty well understood, or at least well documented. I don't know about understood, but well documented. But the most accurate way to describe light, I would say, was to say that light can be either a wave or a particle. We've Up to this point, we had never ever been able to get light to actually behave as both at the same time. It either behaved like one or the other, depending on the circumstance it was in. Again, that's us watching it or us not watching it. That is until the year 2015, which seems very recent, at least it does to me. But in the year 2015, scientists were able to capture this picture. And what you're seeing in this picture is light behaving as both a wave and a particle. And the key here is at the same time. And I'd like you to write that down in your study guide on page 8, just next to the picture. Again, what you're seeing in this picture is light behaving as a particle and a wave at the same time. The operative phrase there being at the same time. I'm going to show a brief video that kind of explains what the experiment was and how they were able to get this image.
In 1905, Albert Einstein made what seemed at the time to be a preposterous claim. Light, he said, behaves as both a particle and a wave. The insight won Einstein the Nobel Prize. So far, several experiments have confirmed that light is indeed a wave and a particle, but not exactly. The problem is that in such experiments, light behaves either as a particle or as a wave. No one has ever found a way to see it do both at the same time. Now, scientists at EPFL have designed an experiment that makes use of the way electrons interact with light to take a photograph of its dual nature. First, the researchers shot a pulse of light onto a tiny metallic wire, basically trapping it there as a standing wave, a wave that doesn't change position over time.
I want to pause really quick just to remind you, we've created standing waves before. Remember, a standing wave is created when a wave that is traveling in one direction meets an identical wave with the same frequency traveling in the opposite direction. And what happens is those waves will interfere and create alternating constructive and destructive interference. So right away, by creating a standing wave with light, they are demonstrating its wave-like properties.
But remember, because of the wave-particle duality of light, the standing wave of light is also made up of particles, the photons. Now here's a question. You need light to take photos, right? But how do you take a photo of light itself? The EPFL researchers figured out a clever way to do it. They shot a stream of electrons right past the wire holding the trapped light, so close that the light and the electrons were forced to interact. Because light is made up of photons, the electrons would hit them and either slow down or speed up. This change in speed can be measured as an exchange of energy packets, or quanta, between the particles. Then, using a specialized microscope that can see electrons, well, this is really what it looks like, the researchers were able to see where this exchange of energy happens along the wire. All that was left now was to take a photo. Et voila! The first ever snapshot of the dual nature of light.
So, just to make sure you're okay with this, right? This right here, this kind of little wavy looking thing that you can see on the edge, that is the standing wave that was created. Again, the wave nature of light. Now, what you see in the middle here are all these little bumps. These bumps correspond to a photon exchanging that little small quantum or that small energy packet with an electron. The bumping, it's not really bumping, it's exchanging energy, but the small quantum, the small energy packet, which Albert Einstein earlier showed us that is particle-like nature. And so there you have it. You have a picture of light that is actually doing both at the same time, acting like a wave and acting like a particle. First time it had ever been done in history in 2015. All right, that concludes this unit. That concludes the traveling light unit. So what you're going to do now is you're going to complete the versatiles, which are on page 9. It's a fairly simple matching. A lot of them are names, and I know a lot of you are annoyed that I'm making you memorize names, but it's kind of crucial in the unit about light because it's a very historically rich unit where we learn a lot about breakthroughs in science and the people who are behind those. So go ahead and complete this. What I'll do is I don't have it in my slides, but I will post a picture of the correct answers. I'll do that on Canvas. And so you can take a look at those. You'll also be able to take a look tomorrow when I get back. So go ahead and do that right now, and then you can kind of breeze through the study guide. If there's anything missing, maybe find a partner and try and get that missing stuff made up. Again, we'll go over all this tomorrow. We'll review, maybe play a game or something like that. And then Thursday, I will have your exam ready for you. And then that'll be it. Thanks you guys for watching, and be good for the rest of the hour. Thanks.